So you got a position vector r of t position function in space. Derivative is rate of change of position with respect to time, if t is your time, right? And that's your velocity. Now, t could stand for some other parameter other than time, okay? So you can still talk about r prime without talking about velocity, but since we are dealing with these things in physics at the same time we're talking about them here, we might as well use the idea of velocity. But whatever your parameter t is, it can define your curve, right? You know, t could be your angle, okay? You know, it could be talking about polar coordinates. We need to talk about that, okay? But right now, we'll think of it in terms of velocity and acceleration, but it generalizes where t could be any parameter you like, including the arc length parameter that we'll talk about, okay? You've already seen it, but I haven't really talked about it. Now, so anyhow, this is tangent to the path, right? And this has components parallel and perpendicular to that tangent, whatever your parameter is, okay? If the parameter is time, then this is velocity, and this is your acceleration. And your parallel and perpendicular components will be your tangential and centripetal accelerations. Okay? So those are the three really important derivatives for motion and for most analysis of space curves. It's all you need to be able to define the osculating circle, but it's going to help a whole lot if we have a unit tangent vector, because how do you determine the components of this parallel and perpendicular to this? You use projections, okay? Dot products. And they're a whole lot easier if you're doing dot products with unit vectors, okay? So we want to define a unit tangent vector, then we want to define a unit vector perpendicular to direction and in the direction of r double prime t, you know, the inward direction. If you're curving this way, we're talking about inward toward the center of the osculating circle, okay? So we want to talk about all that, and we can do that in rather compact fashion. So your unit tangent vector, well, this vector's tangent, obviously a unit tangent you divide the vector tangent by its own magnitude, and you have a unit vector in the direction of motion. And it is, you know, it's a function of t, and I should have written that. But, so that's your unit tangent. Again, if you're thinking in terms of velocities and stuff, it's a unit vector in the direction of motion. So it follows, and you can think through why. I'll let you fill in this blank, okay? The magnitude of your A perpendicular vector sorry, your A parallel vector, that's the easy one. You just dot your r double prime with your unit tangent. Okay? Now that's in terms of acceleration, using that intuitive idea. Okay? And it's, yeah, well, it's the absolute value of this. Okay? Now let's draw a picture. Okay, I'm going to turn the camera off for a minute because then we'll come back and talk about this a little bit. Well, let me draw the picture. You've got your R prime of t, and you divide that by its magnitude, and you've got your unit tangent of t, right? And you've got your R double prime of t. And the way I've drawn it, it's clear that this thing has a component in the direction of R prime and a component in the direction perpendicular to R prime, right? So I can draw this vector and this vector, okay? And for compactness, I'm going to label this A parallel and A perpendicular. Just kind of identifying this with acceleration, okay? And when t is your time parameter, these are parallel and perpendicular components of acceleration. But in any case, this A perpendicular is going to give you a vector perpendicular to your unit tangent, right? So your unit normal, I'm being all colorful here, your unit normal N is your A perpendicular divided by the magnitude of your A perpendicular. So now you've got a unit normal vector. This is a unit vector, this is a unit vector. Okay? Well, let's see how we'd calculate that.